Timescales are important when we're talking about climate change because it answers a lot of questions. These are ones from Westside students about that all had to do with time. How long until cities closest to water are completely covered, or will they be? When will it be fully melted? I believe refers to ice caps. What will our coast look like in 50 years? How fast is this happening? How there have been similar melting periods in the past. Those are all questions that can be answered by timescales. On Blackboard, there are these two movies about sea level rise. And when we start to look at sea level rise in particular, it's really important to know how long it will take, because if it happens slowly, we'll have lots of time to deal with that sea level rise. But if it's happening quickly, it becomes a little bit more urgent, because how do we deal with the people, right? Because most of our population lives near the coast. And so timescales are super important when we're talking about climate change, for not only the effects reasons, but also for causes. So there's two definitions you have to know: a geologic timescale versus a human timescale. So geologic timescale includes entire Earth's history. So it's all 4.5 billion years. When we're talking geologic timescale, we'll use units such as hundreds, thousands, millions of years. If we're talking, so thousands or millions or billions of years, excuse me. If we're talking about a human timescale, that'll be centuries, decades, or less. So this graph here on this page shows both a geologic timescale as well as a human timescale. So the inset here is a human timescale, and then the big graph is the geologic timescale. You'll also notice that this chunk of data right here corresponds with this one, and we can see that it's been stretched out this way and it's been smushed this way. And it's good to know that no matter what, anyone who wants you to believe something can do that to data. So it's always important to kind of keep in mind what's been stretched and smushed and whether it's been cut off, something like that. So in this next example of a geologic timescale, what we see here is this is all of Earth's history. The red line represents the temperature of Earth during these times, and the blue line represents the sea levels. But we're going to focus in on two lines, the red and then this black line. This black line here in the middle shows present day temperature. So this kind of all the way down here, this center line. And if we look at that temperature line, we see there have been periods where it's much cooler, periods where it's been similar, periods where it's been much hotter in Earth's history. And so that's the first thing to notice, that temperatures change over geologic time. But also notice that these are labeled, these temperature extremes are labeled with mass extinctions. Most of the time, here's one that's not, most of the time we see during a temperature extreme, we see that there's been a mass extinction. And so what we can tell is that mass extinctions happen during those times of temperature extreme. So two things to notice on geologic timescale: temperature changes over time, and mass extinctions occur during those periods of temperature extreme. Here's another example of a geologic timescale. Now this one's important again because of that stretching and smushing. Notice how our scale changes per section of this graph. And so, and this slide is from Dr. Donald Wilhite from UNL. But back here we see that this scale goes in hundreds of millions of years, and we can see a lot of variation in Earth's climate. If we then kind of zoom in and expand out a little bit, this one goes by tens of millions of years, and we see that climate kind of start to cool. And then we go into single millions of years, and again we're still cooling off. And then when we get down to thousands of years, here we start to see that variation again. We see that variation of time up and down. And again, this black line down the center is Earth's present temperature. Here, right here where this red arrow is, you'll see this is what Dr. Wilhite refers to as the birth of civilization. On your example that's in your notes, you can just write humans. That's what I did. So humans appear right here, and all of a sudden the pattern changes. Notice how we had quite a bit of variance. It kind of settles down, but it's slowly decreasing. We have some variance through here, but then all of a sudden what we see is that variance really smooths out, and now it's increasing. And so we can tell that, humans are having an impact. There are some links for climate spirals, ice, and carbon dioxide in your notes. And what we see with the climate spirals is that temperature is increasing over time. What we see with ice is decreasing over time, and carbon dioxide is going up, and it tends to concentrate near the poles. And so on a human time scale, a lot of times what we hear as instructors is, we don't see the impacts in our lifetime. On a human time scale, these are all things you can see within the last few hundred years that is impacted by climate change. So keep that in mind, that there are those changes, and I highly encourage you to go click those links. If we look at it per country, you'll notice the United States is kind of right down here at the bottom. We're going to go ahead and play this through. So this starts in 1880, about the time of the Industrial Revolution. We're still seeing lots of blue circles where places are cooler. But then what we start to see is around the 1940s and 1950s, those blue circles are starting to diminish, and those red circles really start to dominate. So especially as we get into the 70s, 80s, 90s, but what you notice about the USA is we tend to be a bit cooler than other countries, and so that's kind of hard when we're one of the big producers, is it's hard for us to really understand the impact we're having. 2017 is where our animation ends, and what we see is that every country is experiencing some sort of warming, and so that's within this human time scale. The other thing to think about when we're looking at timescales, though, is the slopes of lines, because the slope of the line indicates the rate. And so here what we see is we see really dramatic increases with gradual decreases in carbon dioxide cycles. So a dramatic increase followed by a really gradual decrease, a dramatic increase, really gradual decrease. So here's the next really dramatic increase. And if we even go, and so that looks like a pretty steep line, like all of these, but it just goes up a lot higher. If we look at this one, when we zoom this section of graph and we stretch it out this way and we smush it down this way, what we see is that line still goes up. Even if we change our scale, this line still goes up, and it's going up quickly in comparison to the rest of the graph. So the slope of the line indicates the rate. So if we go back to this graph, this geologic timescale graph, and we look at this one instead, and we look a little closer, so we're going to kind of zoom in on this end one. If we look at our estimations for our current status quo, if we keep everything the same as what we're doing right now, notice how 2050 and 2100, we're up almost 10 degrees, somewhere between 5 and 10 degrees Celsius, or Fahrenheit, is the change in global temperature. So timescale, even if you're looking at a geologic timescale or a human timescale, what we see is that humans are making a difference and that the climate is changing. Thanks, warriors.